In this section, we are continuing our work with vectors, looking at the dot product. So the dot product of two vectors results in a scalar, or just a number, rather than a vector. So if you have two vectors, you find the dot product by multiplying the x values and adding that to the y values multiplied. So that's a sub 1 times a sub 2 plus b sub 1 times b sub 2. So for example 1, we're going to find a few dot products here. So for v dot w, that would be negative 2 times 3 plus 2 times 14. So negative 6 plus 28 is 22. V dot V, that would be, we've got negative 2, 2, dot, negative 2, 2. Okay, so we're just doing the dot product with the same vector. So we've got negative 2 times negative 2 plus 2 times 2. So 4 plus 4 is 8. And last, w dot w, we're just doing the dot product with w. So 3 times 3 plus 14 times 14, that's 9 plus, I don't know what 14 times 14, 196 looks like. 205. Properties of the dot product. They pretty much follow properties of multiplication. U dot V is the same as V dot U. U dot V plus W is the same as U dot V plus U dot W. So distribution there. If you multiply 0 vector times a vector, you get back 0. V dot V is actually giving you the magnitude squared. So you're basically, the magnitude would be your A value squared, the square root of the A value squared plus the B value squared. And if you square that, then you take away the square root. So that's what you're getting with V dot V. And then if you multiply U times a scalar, and then, which you would get a vector out of, and multiply that by vector V, then that's the same thing as if you do the dot product of U and V and multiply by C, or if you multiply a vector times C and do the dot product with U. An alternative formula for the dot product that'll be useful to us is multiplying the magnitude of V times the magnitude of W times the cosine of theta. So that'll be useful to us in some cases. So in this, we've got vector U and V, or it looks like in my picture I've got V and W, but that's okay. And so this is really supposed to be V and W. And theta is the smallest non-negative angle between them. Then cosine of theta would be equal to V dot W over the magnitude of V times the magnitude of W. This helps you find the angle between two vectors. So example 2 says, find the angle between the vectors V and W, round to the nearest tenth of a degree. So to find the angle, we'll have cosine of theta is equal to V dot W over the magnitude of V times the magnitude of W. Okay? So we first need to find V dot W. Well, that's just -2 times 3 plus 3 times 4. Gets us 6. Then we need to find the magnitude of V. That's the square root of -2 squared plus 3 squared. Gets us square root of 13. And then we find the magnitude of W. Square root of 3 squared plus 4 squared is 5. So to find our angle, we'll do the inverse cosine of V dot W, which was 6, over the magnitude of V, square root of 13, times the magnitude of W, 5. So you'll put in your calculator the inverse cosine of 6 divided by 5 square root of 13, and you should get approximately, in degrees, 70.6 degrees. And so that's how you find the angle between two vectors. Parallel and orthogonal vectors. Parallel vectors are when the angle between the two vectors is 0 or 180. So the vectors don't have to be on top of each other like you would normally think of parallel. They just have to point in the same direction or in opposite directions. So here V goes this way, W goes this way. V that way, W that way. So the angles have to be 0 or 180. To be orthogonal, that means that the vectors are perpendicular. So that is when the angle between the vectors is 90, just as you would expect. Now you can test for orthogonal by taking the dot product. If the dot product is 0, it means that the vectors are orthogonal. If the dot product is the same as either the magnitudes multiplied or negative the magnitudes multiplied, then the vectors are parallel. So here we want to determine if the vectors are orthogonal, parallel, or neither. So the first thing we need to do is find the dot product between the two of them. We'll have 1.8 times -9 plus 0.3 times -1.5. That gives us -16.65. So we know that they are not orthogonal. If they were, then the dot product would be 0. So next, we'll test to see if they could be parallel. So in order to do that, we need the magnitude of K and the magnitude of S. So the magnitude of K would be the square root of 1.8 squared plus 0.3 squared. And that is 0.3 square root of 37. For S, the magnitude of S is the square root of -9 squared plus -1.5 squared. And that is 1.5 times the square root of 37. Now, these two don't have to be the same. Remember, if we multiply them, then we have to get either the same or the opposite of the dot product. So if we multiply 0.3 times the square root of 37 times 1.5 times the square root of 37, we get 16.65. That is the opposite of the dot product. So that means that these two vectors are parallel. Let's do this with two vectors that are written in rectangular form. So again, find the dot product. We've got V dot W. So that'll be 2/3 times 15 plus negative 12 times 5/6. And we get 0. So that tells us right off that these two vectors are orthogonal. Okay, decompose vectors into two orthogonal vectors. Another way to say this is the vector projection of V onto W. So we're taking a vector and we're projecting it onto another vector in order to create orthogonal vectors. And we denote this as projection, so PROG, with a little w underneath of V. And that says the projection of V onto W, or decomposing the vector V onto W. To do that, we find the dot product between the two, divide by the magnitude of W squared, and multiply by W. And that gives us our new vector. And this is basically just saying the same thing. So, well, let's read through that last part. So, if we find the projection, V sub 1, if that's the projection of V onto W, and V sub 2 is V minus V sub 1, then the vectors V sub 1 and V sub 2 are called vector components of V. The process of expressing these is called the decomposition of V onto V sub 1 and V sub 2. So example 5 wants us to find the vector projection of V onto W. And we write it like this. And it is V dot W over the magnitude of W squared times W. And you could break this up and do those separately. I'm just going to do it all together this time. So V dot W will be 3 times negative 8 plus negative 1 times negative 3. Then the magnitude of the vector W squared, magnitude is square root. So once we square it gets rid of the square root. So we're just doing negative 8 squared plus negative 3 squared. Again, this would have been the square root of negative 8 squared plus negative 3 squared, all squared. So I just took away the square and the square root. That's all I did there. And then we're going to multiply that by W, which is negative 8I minus 3J. Okay? When we do the dot product, we get negative 21, and the magnitude squared is 73. We'll multiply that by negative I minus 3J, and that gets us a bunch of funky fractions. It's 168 over 73I plus 63 over 73J. And so the vector projection of V onto W is this vector right here. Part B says find V sub 1 and V sub 2 such that V sub 1 is parallel to W. V sub 2 is orthogonal to W, and V sub 1 plus, I think that's supposed to say V sub 2 equals V. Yeah, have to change that later. Okay, so V sub 1 and we're using the same vectors here as we did in part A. V sub 1 is the projection of V onto W. And so we just found that in part A. So writing that in component form would be 168 over 73, 63 over 73. Okay, that's the same thing as in part A. To find V sub 2, we want V minus V sub 1. Okay, so V from our problem was 3 negative 1 if we write it in component form. And we're subtracting off 168 over 73, 63, 73. Okay? So 3 minus 168 over 73, if you get a common denominator, or you can put that in your calculator and change it back to a fraction, is 51 over 73. And negative 1 minus 63 over 73 is negative 136 over 73. So we've already found V sub 1, and this would be V sub 2. And last, how can we apply these things? Well, one way to apply is, this is our definition of work. We use vectors to define work. If you ever take physics with calculus as a part of the physics you take. It depends on which physics class you take. But if you take it with calculus in it, then you're going to be doing a lot with vectors. So it says the work done by a force moving an object from A to B, or I don't know what ID is displaced by displacement. Oh, well, that doesn't sound right. Let me look at my notes, make sure I got that right. So moving an object from A to B or is displaced by a displacement vector D is this. Okay, there we go. So work is force times this displacement vector D. Another way you could write it is the projection of F onto D, or the magnitude of the projection of F onto D, times the magnitude of D. And even another way you could write it is the magnitude of F times the magnitude of D times the cosine of theta. So it just depends on which one applies best to your particular problem. And if you use the last one, theta is the angle between F and D. So here's an example. If you've got the force, so we're taking this box and pulling it, so I guess it's got a string attached to the bottom. The work is the force to pull that box times the, I guess you could say, the resistance this way, okay? The displacement. So example 6 says a force of 85 north, or 80, no, not north, 85 newtons is actually what that stands for. Newtons is a unit of measure. So a force of 85 newtons is applied to move an object 20 meters horizontally. If the force is directed 44 degrees upward from the horizontal, find the work done in moving the object. Okay, so we need our force vector. We need the displacement vector, and we need theta. So the force vector is dealing with 85. And it says let's come back to that. The displacement, it says it's to move the object 20 meters horizontally. So the displacement is 20 meters horizontally. That's 20I, because I is the horizontal axis with vectors. And so 85 is the vertical aspect here. So there's your force vector, 85J, and your displacement vector, 20I. And then your angle, of course, is 44 degrees, just like it says. So the work done is the magnitude of F times the magnitude of D times the cosine of theta. Well, the magnitude of F is just the square root of 85 squared. So square root of squared, that gets rid of the square root and the square. So it's basically just 85. And the magnitude of D would be the square root of 20 squared, or 20. Then times the cosine of 44 degrees. So you put that in your calculator and you get 1,223, and we call that Newton meters because we've multiplied the newtons and the meters, so we just call them Newton meters. So the work done is 1,223 Newton meters. And that concludes this section.